Good morning. How are you all?
Good morning, sir.
We were doing exercise 6.1. So 6.1.2 we solved. Okay, so let's do 6.1.3. So 6.1.3. The question is determine all RS such that KRS, okay, complete graph, complete bipartite graph with R and S vertices. This is planar. So, what are the values of RS such that it will be a planar graph KRS? Can you tell? Yeah. So, do you have answer, or you can try? Okay. See. So, what do you know about K33? Is it a planar or non-planar graph?
None.
So, this is non-planar graph. Okay. So, R and S cannot be 3, 3. What do you know about K44? Is it planar or non-planar? So you can check. If you are not sure, then you can check. Like you have four vertex, four vertex. So each vertex is four. Suppose four. Now again join this. Okay, so can you draw this graph without crossing edge? So check. So this is a planar graph or a non-planar graph. K44.
So, non-planar.
So it is non-planar, correct? So what about K22? So two vertex and two vertex. So can you draw this K22 without crossing edge?
Yes, sir.
So it is planar, okay? Because it's right. So it is a planar graph. So we have to determine what about K23? So it is planar or non-planar? So K23 is a planar or non-planar graph?
Planar.
A planner.
Yes, two, one, two, three. So you can join them without crossing edge like this. There is or you can join from here also. Anyway, you can. So you can draw without crossing also. Okay. So it is a planar graph without crossing edge. So it is a planar. So we have to know the result regarding RS. So we are just looking few examples. Okay. So you can decide if you don't know anything. If you already know, that's fine. Okay. What about K12? What about K13? What about K14? So I'm looking for all
Right.
possibilities. So all are planar. Okay. K12, you can simply join. So it is a planar. So it is a planner, it is a planner, it is a planner. Okay, K15, K16, all will be planner. So what you can decide? Why K33 was not planner? Why K4 was not planner? What about K34? Look about K34.
It's a non-planar.
Yes, so it is a non-planner because you have three and you have four here. You have to draw it without the crossing edge. So you can think of drawing, but this is possible. Like you can join here. No, you can join here, no problem like this. Okay. And the problem is like, how will you join if you do this? How will you join crossing this? You have to cross the edge. So it is non-planar. So K34 is non-planar. So why it is? You can notice few things. So K22 is planar, K23 is planar, K12 planar, 13 planar, K14 planar. But K33 is not planar, K44 is not planar, K34 is not planar. So one thing you will be convinced by this result that KRS is a planar graph if and only if minimum of RS. So whichever is the minimum, है ना? So one will be less, other one is a larger, or both may be equal, no problem. So the minimum of both must be less than equal to 2. So that means you can also say that is at least one of, so at least one of RS must be either 1 or 2. Either 1 or 2. So out of R or S, at least one must be 1 or 2. Okay, so at least one must be 1 or 2. So that is the result. Okay. So next example, next question we have 6.1.5, and this is saying prove that a plane graph has cut vertex. So prove that a plane graph. Okay. So plane graph has a cut vertex if and only if, so if and only if its dual has cut vertex. Oh, I think it's not prove that. It's a prove or disprove. Okay, so prove or disprove. So statement is prove or disprove. This is a statement. A plane graph has a cut vertex if and only if its dual has a cut vertex. So if a graph G has cut vertex, then its dual graph G star will also have cut vertex. So this it's if and only if. Okay. So this statement is true or false. You have to tell. And then if true, then prove. If false, then give example. So what do you think? You take any one graph and try to see. So plane graph which has cut vertex, if and only if its dual will have cut vertex. Yes, what do you see? It's a true or false? So look, let's make one graph with cut vertex. Okay. So you can simply make a, let's take a tree like this. Okay. You take this tree, or this is just equivalent to this one. You can write like this also. So this is graph G. Suppose this is graph G. So tell me, what is dual of this graph? So how do you find the dual of a graph? So you first check this graph G divides the plane, or yeah, divides the plane into how many parts. So see, graph G divides the plane into how many parts?
One.
So it's a one both side, है ना? Just one part x. So you will have just one vertex in the G star, because in dual what you do, you take the face or region in G as the vertex in G star, and then corresponding to each edge in G you have an edge in G star. So corresponding to this edge, so let me call it ABC. Okay, so corresponding to this AB, both side of the edge AB has XX, so there will be edge from X to X. So that's a loop. Again look at AC is an edge and both side are region X only. So again we will have one more loop like this. So this graph G star has no cut vertex. Okay, so this is the example against the statement. So means the statement is incorrect. Okay, so statement is incorrect. So it's a false statement. So statement is false. And you can write the result like, so dual of, like you can say, trees, okay, have at most two vertices. Yes, you can say exactly one. So in the tree divides the plane into one part only. Okay, so it will have one vertex and that will create loops. So there will not be any cut vertex in that. So statement is false. So here you can see, because in a tree, let's say T, you can say, है ना? Or you can write a tree T has cut vertex, but its dual T star. Okay, its dual T star has only one vertex, है ना? And joined with loop, or you can say directly it has no cut vertex, because if you convert the T into T star, so in T star you will see there will be only one vertex, and that will have loops, so it will not be a cut vertex. Okay, so next question is 6.1.8, and the question is, prove that, prove that every simple planar graph, so prove that every simple planar graph has degree at most 5. So prove that every simple planar graph has degree at most 5. Okay. So how will you prove that every simple planar graph has degree at most 5? So we'll prove it by method of contradiction. So we will prove it by using method of contradiction. So we use method of contradiction. Okay. So what do we do in method of contradiction? The thing we have to prove, we take the opposite, we assume the opposite thing, and later on we prove that some contradictory thing happens due to our assumption. So we prove that assumption was wrong. So we have to prove that every simple planar graph has degree at most 5. Okay. So we'll start with that. Suppose G is a planar graph. G is a planar graph. Planar simple graph. You can do simple planar graph. So G is a simple planar graph. So suppose G is a simple planar graph having the degree, okay, degree of every vertex. So degree of every vertex at least 6. So I'm taking degrees at least 6. So we have to prove that each vertex has degree at most 5. Okay. So actually graph has a degree at most 5. So we took the contradiction of that. We took that G is a simple planar graph having degree of every vertex at least 6, 6 or more than 6. Okay. So what do you know about degree sum formula? So degree sum formula says 2e is equal to sum of degree of each vertex. Okay. Sum of degree of each vertex. 2 times sum of degree of each vertex. So 2e is equal to sum of degree of each vertex. So we took that every vertex has degree at least 6. Okay. And what are the total number of vertices? We take it n. Okay. So suppose G has n vertices. So number of vertices is n. So this quantity is going to be more than equal to 6n. N are the number of vertices and 6 is the degree of each vertex. So degree sum going to be more than equal to this 6. So let's see that. So 2e is more than equal to 6n. But what we want to get some contradiction. Okay. So cross 2 both sides. So divide by 2 both sides. So you will get e is more than equal to 3n. And what do you know about this? So you know that if G is a simple planar graph, you had result already. Planar graph, E is less than equal to 3n minus 6. You know that? Actually, 3n minus 6 itself is less than 3n. So that's why E must be less than equal to 3n. But what you are getting here? Oh, not this is strictly less than, okay? Because 3n minus 6 is strictly less than 3n. That's why E is strictly less than 3n. But you are getting the opposite thing, okay? So this is a contradiction to the statement or to the condition. You can say E is less than equal to 3n minus 6. So you already know that E is going to be less than equal to 3n minus 6, but it is saying E is more than equal to 3n. That is contradiction. Okay, this is strictly less than 3n. So in actually we know that if G is a simple planar graph, then E is going to be less than equal to 3n. But you are getting more than equal to 3n. That is a contradiction. That's why our assumption is wrong. Hence, so therefore our what we assumed was wrong. So our assumption is wrong. Okay, and therefore, so the statement is correct. Okay, so you can write. So every simple planar graph, so every simple planar graph has a vertex has a vertex degree at most 5. Okay. So we use the method of contradiction. So if you have doubt, you can ask. Just assume that each vertex has degree at least 6. Then using degree sum formula, we get 2e more than equal to 3, 2e more than equal to 6n. Means e is more than equal to 3n, and that is contradiction to the fact that e should be less than equal to 3n minus 6. So that's why our assumption were wrong. So next question is 6.1.9, and this question is, so prove that prove that every every simple planar graph, okay, prove that every simple planar graph with fewer than, so less than 12 vertices. Okay, so prove that every simple planar graph with less than 12 vertices has a vertex, so has a vertex of degree at most 4. Okay, so every simple planar graph with less than 12 vertices has a vertex, so there is a vertex, okay, of degree at most 4. So 4 or less, degrees 4 or less. So how will you approach? Again we'll use a contradiction method. Okay, so we have to prove that there is a vertex of degree at most 4. So I will assume that no vertex has degree at most 4. Means every vertex has degree at least 5. Okay, so we'll assume. So proof. Again we use method of contradiction. Method of contradiction. So we'll assume that, so suppose simple paragraph with less than 12 vertices has, so suppose every vertex, okay, has degree at least 5, okay, in a simple planar graph, in a simple planar graph, simple planar graph with less than 12 vertices, okay, less than 12 vertices. Now you assume that each vertex has degree 5. Okay, so like you have given what, you have given that it has vertices, number of vertices less than 12, and you assumed each vertex has degree at least 4. Okay, so let's apply that degree sum formula. Degree of vertex b of graph G. So you assumed each vertex has a degree 4, so this is more than equal to 4n, right? Oh sorry, at least 5 now. You assume that degree of each vertex is at least 5. Okay, 5 or more. You have to prove 4 or less. Okay, but you assume the opposite, contradictory statement. So and then you get 2e is more than equal to 5n. And what is your 12, what is your n? N is less than 12. Okay, and what you know about this e, since it is a simple planar graph. Okay, so this is the one result you used according to your statement. And since graph G is simple planar graph, simple planar graph. So what do you know that if it is a simple planar graph, then E has to be less than equal to 3n minus 6, right? So if you multiply 2 both sides, 2e is less than equal to 6n minus 12. Fine. So 2e is less than equal to 6n minus 12. Now you combine these two inequalities, first and second. Okay, this first and second. What will you get? So one says 2e is more than equal to 5n, and other say it is less than equal to 6n minus 12. So now 5n is less than 2e, 2e is less than equal to this. So 5n is less than equal to 6n minus 12. So 5n is less than equal to, so what do you get? You take 6n this side. So 5n minus 6n less than equal to minus 12. So minus n less than equal to minus 12. You multiply minus both side. Inequality will change. N is more than equal to 12. But what was given to you? That it has vertex less than 12. So which is contradiction. So this is contradiction to the fact. So this is contradiction to given fact 10 less than 12. Hence, what we assumed is wrong. Hence, our assumption is wrong, and that's why it has at most 4 degree. Second, you copy a second that at most 4 degree. So, are you getting the point? So, we are proving using contradiction method. So, what we have to prove, we assume the opposite thing, and then at the end, we get some contradiction to the given fact, and that's what then we say that our assumption is wrong, and then what was given in the question is correct. Okay. And the next question is 5.1.10, sorry, 6.1.10, right? 6.1.10. So this question is prove or disprove, okay, prove or disprove, there is no simple, okay, bipartite, so there is no simple bipartite planar graph. So there is no simple bipartite planar graph with minimum degree at least 4. Okay. So minimum degree at least 4, कम से कम 4 होगा डिग्री. Okay. So ऐसा कोई simple bipartite graph हो ही नहीं सकता, मुझे ये प्रूव करना है. Okay, you have to decide true or disprove. Sorry. So you have to decide first is true or false. So there is a no simple bipartite planar graph with minimum degree at least 4 and minimum degree 4. Okay. So you know about simple bipartite graph. Actually, in simple bipartite graph, what happens? This is actually triangle free. Actually, simple bipartite graph is triangle free. So each face will have length 4 or more. Now it will not have face less than 4. Length of face actually. Okay, so it does not contain a triangle. So length is at the most, and you also know that it does not contain any odd cycle. So bipartite graph does not contain any odd cycle. So it is a triangle free, you say. So we have to prove there is no such. Okay. So this statement is actually true, and let me write the proof. So what we have to prove? We have to prove there is no simple bipartite planar graph with minimum degree at least 4. Minimum degree is at least 4. So since G is simple bipartite graph, bipartite means triangle free. Okay. And if you remember theorem 3, So theorem 3 was the extension for theorem 2. So in general, if it is only simple planar graph, then E is less than equal to 3n minus 6. But if it is triangle free or bipartite, then the result was E is less than equal to 2n minus 4. Where graph is a triangle free. So you have this result. So that's what E is less than equal to 2n minus 4. So you can decide here 2E is going less than equal to 4n minus 8. Okay. So 2E is less than equal to 4n minus 8. Okay. So number of stages is at most 2n minus 4, and you know that 2E is equal to summation of degree of each vertex. So that's what, and that sum of degree is less than equal to 4n minus 8. Okay. So from here you know that both are equal, and you get that this quantity is less than 4n minus 8. Sum of degrees. Okay. So like what do you know that sum of all degrees is actually less than equal to 4n minus 8. So what about the average degree or average degree of a vertex? What about average degree of a vertex? What about average degree of a vertex? So how do you find average degree? Average degree actually degree sum. So sum of degrees of all the vertices, like n vertices are there. If you divide by n, so you will get average degree sum, or average degree of one vertex. Okay. So like average, average degree sum I'm finding. So degree sum of all degrees divided by n, like this I'm doing. Okay, sum of all degrees divided by n, and what will you get there? So this was since degree sum is less than 4n minus 8, you divide by n, it is 4 minus 8 upon n. So average degree, so there are n vertices. Okay, sum of all the degrees of vertices, sum of all the degrees of all vertices is 4n minus 8, less than 4n minus 8. Now I'm finding average degree, that is less than 4 minus 8 by n. You can take equality here. Okay. So what do you know relation between, like you have n vertices, so each vertex has some degree. So minimum degree and average degree. So which one you will find smaller? Minimum degree and average degree. Which one will you find smaller? Suppose you have 100 numbers, you find their average, and you look for the minimum number in that 100 numbers. So which one you will find smaller? Which one you will find larger? Yes, this is strictly less than 4. Tell me, you have 4 numbers. Suppose 1, 2, 3, 4. You take only this, and you take their average, and you take the minimum number of that 4. Decide. Tell me which minimum and average. Which one you will find smaller and which one is larger?
Minimum is smaller than average.
So very obvious thing, right? Suppose 1, 2, 3 I have. So I will take the average. Then 3 plus 2 plus 1, 6. And upon 3, 2 is the average. And minimum is 1. So obviously it's a minimum. So minimum data is obviously will be less than the average. Okay. And this average actually, average degree is less than 4. So what do you decide from here? That the minimum degree is less than 4. And that's what we wanted to prove. So what we proved? In a simple bipartite graph, the minimum degree is at least 4. Matlab 4 or more than 4. And we have to prove there is no such graph. Okay, so we proved that in every simple bipartite graph, minimum degree is going to be less than 4. So in every simple bipartite planar graph, so in every simple bipartite planar graph, minimum degree. Okay, so minimum degree is less than 4. Hence, there is no simple bipartite. Okay, there is no bipartite planar graph with minimum degree at least 4. Okay, there is no such graph, because in every graph degree is going to less, the minimum degree is going to be less than 4. So minimum degree cannot be 4 or more. So there is no such graphs. Okay, so till now you have any doubt?
No, sir.
So now here we completed chapter 6. So we'll start here chapter 7. So chapter 7 is the last chapter in your syllabus. Okay. So chapter 7 is actually the name of chapter is ages and cycles. Ages and cycles is the name of the chapter. So article 7.1 is actually line graphs and age coloring. So line graph and age coloring. So we have seen graph coloring, vertex coloring. Okay. So line graph, and here we'll see age coloring. So line graph and age coloring. So the first topic we'll discuss here is age chromatic number. Like you already know the chromatic number of a graph and chromatic polynomial also. So here we'll discuss age chromatic number. Age chromatic number. Second, we'll discuss one factorable graph. One factorable graph. And then we have class 1 and class 2 graph. Class 1 and class 2 graph. Okay. So the course outcome in this chapter is, so it is and discuss define and discuss line graphs. So define and discuss line graphs, age coloring. Okay, so line graphs, age coloring, and study the various aspects of Hamiltonian cycle. Hamiltonian cycle. Okay, so first I will start with the line graph. So what is a line graph? Okay, so first definition. Is a line graph. Okay? So line graph is a simple graph whose vertices are the edges of G. So like you have seen the dual graph, okay? So similar to that, you can find a line graph responding to a graph. So the definition is the line graph of G written as L of G. is simple graph. Okay, is simple graph whose vertices are the edges of G. So look, in the line graph, the vertices will be edges of G. Okay, so edge and vertices will be interchanged now. So the edges of G will be vertices in line graph with EF. Okay, EF is edge in line graph. So actually EF is in line graph. Okay, so E and F actually separately are the vertices in line graph, and that EF vertices was edges in G. So edge of graph G will be vertex in graph line graph. Okay, so E is one vertex and F is the other vertex in line graph. So E and F are edges in G. Okay, so with EF together I'm writing EF is edge in line graph when E and F have a common endpoint. Common endpoints in G. So two edges in G. Okay, so you will take that as a vertex and you will join an edge in line graph only if they have a common endpoints in G. So for example, so you will understand better if I have this. So see, a graph G has like, so this is D, E, F, G, H. So D, E, F, G, H are edges in graph G. So this is graph G. Okay. So E, D, E, F, G, H are edges in graph G. And you want to write line graph of G. Okay. LG. So line graph of G. So D, E, F, G, H. These are vertices in line graph. Okay. So edges of G are vertices in line graph. Now, how will you join that in a line graph? So you will make an edge if the two edges in graph G has a common vertex. So look at edge D, and look at edge E. Do you see there is any common vertex in between them, D and E?
Yes, sir.
So you will have one edge between DE because D and E have one common vertex. Again, D and F has one common vertex, so there will be an edge between D and F. D and G has also one common vertex, so we will have an edge between D and G because D and G has one common vertex. E and G also have common vertex, so we will make that. F and G also have a common vertex, so you will make that here. G and H has one common vertex, so they are sharing a vertex, so you will make one edge. H and F also has one vertex. Okay, look at F and E. So F and E also has a common vertex. So this is a line graph. So in line graph, what do you do? The edge you will make as vertex. Then you will see if two edges in G have a common vertex or they are sharing vertex. So you will make an edge in line graph. Okay. So fine. If you have any doubt, you can ask. So like if I ask you, suppose this is a graph G, okay? So what is the line graph of that? Can you draw? So please draw and tell me. So like D, E, F, G. There are four edges. So you'll make D, okay, E, F, G. Suppose like this. So you see there is a common vertex between D and E. That's why you will have edge. One vertex will be DF. So this one vertex will be FG, FG, and one vertex between this. The same graph you see here, right? So just edge in G you make vertex, and then just you see if two edges in G share a vertex, then you make an edge in line graph. So the next topic is edge coloring. So earlier we were coloring vertices, now we'll color edge. Okay, so edge coloring. So like for the example of like exam scheduling problem or committee scheduling problem, we have seen we were using vertex coloring concept, to schedule meeting slots, or exam slots. We use edge coloring problem when we have so like we say that when the object being scheduled are pair of underlying elements. So first, let me discuss one example. So like if we have suppose in a league with two n teams, so we are like arranging a league match or league in which there are two n teams. Okay, two n is an even number, so two n teams. We want to schedule games so that each pair of teams play a game. So each pair of teams, okay, play a game, but each team plays at most once a week. Okay, so let me write the problem. So before writing the definition, so you can write also like the problem of exam scheduling and exam date scheduling or exam scheduling है ना, or meeting committee meeting scheduling, right? So we were using or committee, so committee meeting schedule. What we were using? We were using vertex coloring. Okay, we were using vertex coloring. But now is coloring the problem arise. So is coloring problem arise when the objects, okay, when the objects being scheduled, so objects being scheduled are pair of underlying element. Okay, so like for the pair of some elements. So let me discuss one example. Okay, so example is like A is coloring for K2n, the complete graph with 2n vertices. Okay, so A is coloring for K2n. So in a league with two n teams, okay, we want to schedule. Okay, so we want to schedule games so that each team or each pair of teams. So you make pair. So each pair of teams plays game. So each player or team plays a game. Okay, but each team plays at most once, at most once a week. Okay, so we have to schedule a match for each of the two end teams such that each pair. Okay, so every pair of team get to play, and each team plays at most once a week only. Okay, so see, there are two end teams. Okay, so one team have match with how many remaining teams? So how many matches one team will play, or each team will have match with how many teams? Yes, there are total two end teams. Okay, two end teams. So one team will get to play match with how many teams?
2n minus 1.
2n minus 1.
Yes, two and minus one teams. Okay, so two and minus one match each team will play actually. So you can write since each team must play with two n minus one other teams. Okay, so each team must play with two n minus one other teams. So the season, so that match season or league season, last at least two n minus one weeks. You know why? Because each team will get to play only one match in a week, and each team has to play with other two n minus one teams. So season lasts at least two n minus one weeks. Okay, it will take at least two n minus one weeks. Okay, and the game of the game of each week form. So game of each week must form must form a matching. Okay, so game of each week and a must form a matching. So you can match so that like first team get to play with second team, third team get to play with fourth team, fifth team get to play with sixth team, like that. Okay, so every team has to play only one match. Okay, so you have to form a matching such that each team get to play once in a week, and you have to arrange match for all pair of teams. So what we can do, we can schedule the season in 2n minus 1 weeks. Okay, if and only if, so we can schedule season in 2n minus 1 weeks if and only if the age set, okay, the age set that we denoted by e of k to n, the age set this is partition into 2n minus 1 matching. Okay, if we can do that, then we can schedule that. So like I have as k to n is 2n minus 1 regular graph, right? K2n is what? 2n minus 1 regular graph. So this must be, or there must be a perfect matching. Okay, so for example, let's take one example. So like in place of K2n, you consider K4. Okay, so K2n, so you consider K4. Okay, so means we have four teams. Okay, and we have to arrange matches. So how will you do the perfect matching? So you know about K4. Sorry, this is K4, A, B, C, D. So one week you can do what? Once you can do, right. So get a match between AB and one match between BC. This is the first match. Okay. So week one you can do like this. In second week, what you can do? You can get a match between AB and DC. So week two you can do this. And what about third week? Third week you can do this. So match between AC and BD. Okay. So how many weeks you will take to play match between four teams, such that in a week only one team will play once in a week only, and each pair of teams get to play. So you will take 3 weeks. Okay. So week three you can do that. So this is the perfect matching for K4, and you can complete these matches in 3 weeks. So I will continue this example in the next class. So I will stop here today and I will continue next class. So any doubt you have?
No, sir.
Okay, thank you everyone, and we'll see you next class.
Thank you, sir.